Yeah, thank you. So let's start with the agenda for this talk. In this talk, we will talk about fetching provider algorithms. For that, we will talk for a short while about what is a provider algorithm. We will talk about the classes of provider algorithms. What is algorithm fetch actually? There will be some short explanation of library contexts and explanation about implicit and explicit fetching of algorithms, algorithm properties and property queries. So what is a provider algorithm? It's basically a set of function calls into the provider that supports a particular functionality. It can be a crypto algorithm, such as signature, digest operation, symmetric cipher, and etc. It can be also auxiliary function. So that's a non-cryptographic function that supports the operation with, for example, keys. You can have a key encoder, key decoder, key store, or key manager. Each provider can support a single, but more usually it will support multiple algorithms. The algorithms are identified by an operation ID and a set of names. The operation ID is not used by applications directly. It's something that the libcrypto handles for you. More details about providers are on this one page. So here are the classes of provider algorithms. I am not going to read all of these, but you can see that there is always some, for some algorithm type or algorithm class, there is always a libcrypto object and the provider operation. We have digest, symmetric ciphers, MACs, KDFs, key exchanges, asymmetric ciphers, key encapsulation, signatures, random number generation, key management, including key generation, encoding, decoding, and store management. So what is an algorithm fetch? It's actually a retrieval of this set of function call addresses from the provider to libcrypto object. That libcrypto object was listed on these previous tables. They are those EVP-MD, EVP cipher objects, which were there already with previous versions of OpenSSL. But there are new objects like EVP signature, OSSL decoder, and so on. These objects, or internally, those function call addresses are cached to speed up things for later fetches. And the selection of the algorithm implementation from loaded providers is based on operation type, which is implicit in the concrete fetch function, such as EVP-MD, it will be OSSL op digest. Then there is this algorithm name for digest SHA-256, SHA-3-256 for KDFs. An example is HKDF, PBKDF2, and so on. And there is also the property query, which I will cover in later slides. So if all these things are equal, operation type, algorithm name, and property query, there is no defined particular order of preference, such as like first algorithm from the first provider that was loaded or so. It's not defined. It can be any order. Example of algorithm fetch in code, you can see it here. It's like EVP-MD fetch call. The first argument is libctx. That's the library context I will also talk about later. Then there is the name of the algorithm and the property query. These objects are used in respective operation init functions. So EVP-MD, you will use EVP-MD in EVP-digest init. EVP-KDF, you will use in EVP-KDF init. In some cases, these explicitly fetched implementations are not used directly. There are currently no init functions that could use these fetched objects. You can still fetch EVP signature, for example, or OSSL decoder, but you cannot pass that to init function. But still, these objects provide you functions to query their attributes, such as name, description, some gettable or settable parameters. And in addition to that, this might be directly usable in future versions of OpenSSL. So there might be new init calls that will get these objects as parameters. So now I want to cover the library contexts. The library contexts are the OSSL libctx objects, which are opaque to the applications. They hold data structures mostly related to providers and fetch algorithms. Currently, as far as I know, it's like really focused on storing those providers' data structures, provider-related data structures, but there are plans to make them to hold more data that is currently library global in future. These library context objects provide isolation of provider-related configuration for unrelated users of libcrypto. Typically, you can use them for in your applications. You can use multiple library contexts in your application. Typical use is when you need to use in some special part of the code you need to use some algorithm that could be otherwise disabled by the global configuration. For example, by enabling the FIPS mode. Or you can load the provider in separate library context. For example, for the legacy functions, you will load the legacy provider. Another use case for library context is the isolation of provider configuration from library callers. For example, the software HSM module provider wants to call the OpenSSL functions or algorithm implementations from the OpenSSL library itself. And what would happen if there was no separate library context used? It would call, for example, it would when somebody asks or some caller asks the HSM provider to compute some RSA computation, it would call back into libcrypto to do this computation, but that would again call back into the HSM provider, and that would be an infinite recursion. But of course, if it has some separate library context, it will not load itself into this context, and everything will be fine. So to create and release a library context, you use these OSSL libctx new and free calls. These objects are not ref counted, so you need to release them only when they are no longer used. There is probably very useful call OSSL libctx load config, which you can use to apply a provider configuration in a configuration file to a given library context. We have two different default library contexts. One is the global default one. It's actually one that's created during initialization of the library implicitly. This context you can get by calling OSSL libctx get zero global default. And then there is also thread local default library context, which is basically a pointer to the global default initially, but it can be overridden by applications by calling OSSL libctx set zero default. That's useful because not every library call in libcrypto currently provides a way to specify the library context. So by using this, you can temporarily override the default library context that's used by these functions, and then you can switch back to the global default. So let's cover the implicit and explicit fetching now. So explicit fetches were described in previous slides. These are those EVP MD fetch calls and other fetch calls. But there are also implicit fetches that happen during the operation init. Typically, those happen when you use these constant EVP MD, EVP cipher objects like EVP SHA-256, EVP AS128 CBC. These calls don't fetch anything. Those constant objects are just placeholder for this SHA-256 or other algorithm name string that's inside them. And these, so when you pass this constant EVP MD or EVP cipher object to EVP digest init or cipher init, during this init call, it will implicitly call EVP MD fetch or EVP cipher fetch. That has some implication, and that's the fetch is like although it's all the function sets are cached, it's the fetched object needs to be created, and there's some performance overhead with associated with this. So usually, if you used explicit fetch, these explicitly fetched objects can be used in multiple init calls, but the implicit fetch will always call the explicit fetch during the init, or call that. So it's best to avoid implicit fetches for best performance if possible. There are on the other hand, there are also implicit fetches which happen as part of these EVP key operations. For example, the EVP key sign init implicitly fetches EVP signature algorithm, which is appropriate for this given EVP key. But the performance overhead is not so high to be actually noticeable for asymmetric algorithms. That's thanks to the caching and other things. It's not a problem for asymmetric algorithms. There are, on the other hand, there are also composite algorithms which are symmetric, like HMAC or KDF or other similar composite algorithms. And these implementations or implementations of these algorithms usually need to fetch some sub-algorithm inside the provider implementation. So there is also kind of implicit internal fetch here. To to avoid problems or to improve performance with these internal fetches, you can do some workaround. You could duplicate the semi-initialized context. So for EVP MAC, EVP HMAC or HMAC implementation of EVP MAC, you can fetch the HMAC, then you can create a new MAC context, set the parameters with the name of the hash that you will use, and then you duplicate the MAC context, so you can and use the duplicated with the init operation. So internally, the fetch happens during the set parameters set params call, and by using the duplicated context, you avoid doing the fetch again and again. The thing is that, of course, this has some overhead by itself because you have to duplicate. So it depends on a concrete use case whether this is useful or not. Now about algorithm properties. Each algorithm implementation can have a set of name-value pairs, which are called properties. Some property names have a predefined meaning. Those names don't contain a dot. It's still possible by provider authors to set values for those predefined properties, but they cannot add new ones. They can add only those that contain a dot, and they can be added freely, and the definition of the meaning for such properties is the responsibility of provider authors. Property names are internally converted to lowercase. Property values can be strings or numeric, and unquoted string values are converted to lowercase as well. If you quote them, they are kept as is. Yes and no are special string values that indicate true or false. Here we have some examples. We have fips equals yes, this is fips property, which is predefined, meaning that this is some fips approved or allowed algorithm. If it has the value yes. Provider equals default. This is again predefined property that means that this algorithm comes from the default provider. It's actually not mandatory to for third-party providers to provide this property, but it's a good convention to do so. Then there is fictional example of some numeric property, pkcs11 provider dot slots. That's provider defined, and the meaning is also provider defined. So we have these properties, and how do we use or how do we match on them or select algorithms by them? So a single provider can have multiple implementations of particular algorithm, but more usually there can be multiple providers loaded. And we use this property query, which is a string. We use it to select among multiple implementations of the same algorithm during fetching. Simplified syntax, you can see it here on the slide. The question before name marks preferred but optional property. So you can match like for equals or non-equals, and there is also the minus name, which I will talk about later. So we have actually also a global default property query. This is not library global, it's global per library context, and it's applied to all algorithm fetches, including those implicit ones within a given library context. It can be set with a config file. Again, the OpenSSL conf shows the section which contains the initialization or the values for that apply to as a default configuration of OpenSSL. The ALK section marks the section that contains these default properties, so the default properties value is then applied as the global default property. Or you can set this global property query by using EVP set default properties call. And then there is a local property query, and that's the value that you pass as the third argument to those fetch functions. Or it can be passed for those algorithms which are complex, which are composite. You can pass it as OSSL param to be used in the internal fetch in the provider. This local property query is merged with the global property query by merge operation, which means that the values of the same properties are overridden, but the rest of the values is untouched. And you can use this minus name syntax to remove a property from the resulting query. Here we have some example. The global property query is provider not equals pcases 11, pips equals yes, which means this will prefer algorithms from a provider that's not pcases 11, that's the question mark. And the algorithms must be FIPS approved or allowed, that's the FIPS equals yes. But the local property query for some particular fetch is minus FIPS question mark provider equals default. This will basically drop the property FIPS that this local fetch does not require the algorithm to be FIPS approved, and it will prefer actually the implementation from the default provider. So this is the resulting query is question mark provider equals default. If there was some other property, like, I don't know, some provider defined property in the global property query, then the local property query would keep it there. It would be still there in the result. Yes, there is this node that I've told you before, that the provider property or FIPS property is not mandatory. Like the third-party providers don't have to have them, set them on algorithms. So, but usually they will do it because it's good convenience. And that's it. Thank you.